Thank you, Chris. Thank you, Hackaday. And thanks everybody for coming. It's really exciting for me to get a chance to do this talk. It's something that I've been thinking about doing for a long time, and I haven't done it, mostly because I go to a lot of conferences in the information security community, and that's not really the right audience for this talk. The audience for this talk is people who have made a circuit board before. How many of you have made a circuit board before? Yeah, all right. How many of you want to make something that's RF? Excellent. Okay, so if you answer those two questions, then you are the target audience for this talk. I wanted to kind of share my experience and how I've made circuit boards that are RF designs, and how you can do that too. So now my qualifications, just to be perfectly clear, my qualifications are that I've made some RF circuits. I am not an expert RF engineer, not at all. I do not have an engineering degree. I'm simply a guy who's made some RF circuits and made them work. And I want to share with you how I have done that. So this isn't necessarily, I'm not going to talk about the best way or every way that you can create RF circuits. I'm going to talk to you about the way I create RF circuits. So some of my projects are up here. Probably the most famous is HackRF 1, which is a software-defined radio platform. And we're going to talk about these designs in some detail. Probably not HackRF 1 unless I end up with a whole bunch of extra time I wasn't expecting. We probably will not go into that one in great detail just because it's more complex and would require a longer period of time for us to actually delve into its architecture. But everything that we're talking about today, everything that I'm going to present is represented in all of these designs, including HackRF 1. Even though it's more complicated than the others, it is made up of simple parts. And those simple parts are things that I'm going to talk about today. So the traditional approach to RF circuit design involves a lot of knowledge. You need to have a lot of books on your shelf, and you need to refer to them often. And you also need a pile of tested equipment. And some of this stuff can be very expensive, even if you do find it on eBay. And we get all these ideas like S parameters and Smith charts and Q factor and VNAs and RF transistors and many other scary letters that present themselves when we look into RF circuit design, and I think it scares a lot of people off. I talked to a lot of people who said, well, yeah, I've made a few circuit boards, but I've never done RF. That's black magic. And it's really not black magic. In the vast space of all the different possible RF circuit designs you could create, there is a large, significant subset that is very easy, very accessible, and you don't have to deal with any of these things in order to start working with RF and start making your own RF circuit designs. So there's a simpler way, and that's what I'm here to talk about today. The simpler way is what has led me to be able to produce successful open source hardware designs that are RF circuits. So this is the core of the talk right here. If there's one thing you get out of this talk, it is these 5 rules. These are my personal 5 rules for RF circuit design. Now, this talk is going to consist more or less of 3 parts, and that's going to be part 1 is going through these 5 rules in detail. Part 2 is looking at some examples from my own designs that can show you how I have put these rules into practice. And part 3 is going to be talking about components and how do you select components for your design. That's what this talk will consist of. So let's dig right into the 5 rules. The first rule is use 4 layers. Use a 4-layer printed circuit board. And it should look like this. Put RF signals on the top layer, and then just below it there should be a ground plane. And then on the 3rd layer, you should have your power supply. And on the 4th or bottom layer, that's where you put any signals that don't easily fit into the top layer, but not RF. Keep your RF on the top layer. Now, I know there are people in the room who are thinking, but can't I do 2 layers? I like doing 2 layers. Like, can't I get away with it with this one design that I have? Can I maybe do this 2-layer RF thing? And I say, yeah, sure you can, but you better start reading. And you better have a pile of test equipment so you can figure out why your design isn't working, or fix it, or make the performance what it should be. We're not talking about that stuff that I consider advanced topics in RF circuits. So maybe you could get away with doing some 2-layer RF circuits. But the easy way is to go with 4 layers. Go with 4 layers, follow this type of stack up where you have a ground plane that is very close to your top layer, and you have your RF circuits, all your RF signals are on the top layer, and things will go so much easier for you. So that's rule number 1. Just use 4 layers. 4-layer PCBs are very easy to get assembled these days, thanks to our friends at Osh Park and other prototype assembly houses. It's not that expensive, it's not that time consuming to get 4-layer PCBs done. I just ordered some, I think it was in early November, that I have with me today, already delivered to me and assembled. So, but before I came here, so it only took a couple weeks, and I had some 4-layer PCBs, an RF design that actually is featured in this presentation because I had it in time to do that, even though it was just done a couple weeks ago. So, do 4 layers. It makes your life a whole lot easier working with RF. And it's pretty accessible to be able to get 4 layers or even more layers these days in a PCB. So use a consistent stack up. Stack up matters, and by stack up I mean how that PCB is physically constructed. Like, how thick is the substrate between layers 1 and 2? How thick is the substrate, and what are its properties between 2 and 3 and 3 and 4, and how thick is the copper, and that sort of thing. And if you use the same PCB house all the time, then that's not a problem. But if you start a design with one PCB house, and then the next time you get that design built, you use a different PCB house, you better make sure that they use the same stack up that your first PCB house did. You want to make sure that that's consistent. Dedicate the entire inner layers to unbroken power supply planes. The entire layers. Layer 2 is just ground. Layer 3 is just power. That's it. Don't put anything else on those layers. I know you think, oh, it's all that wasted area where I could be running things. And no, if you really need extra traces that can't fit in your top or bottom layers, go to a 6-layer design. Go to an 8-layer design if you absolutely have to, rather than break up your ground plane or break up your power supply plane. Really, this will make your life a whole lot easier. Everything will work right if you have unbroken power supply planes. And keep the RF signals on the top. Don't run them through vias. Don't do anything complicated with them. Make your RF signals as simple as possible, and we'll talk about that more later. The second rule, use integrated components. Use the most integrated component you can for your design. That means you'll be looking at RF ICs, integrated circuits for radio frequencies. There is a huge array of RF ICs available today. They're wonderful. And, but it also goes for other types of components. Things like baluns and filters, passive components, not active circuits, that are available as sort of a monolithic or an integrated package. These things are available today, and I highly recommend that you use the most integrated component that you possibly can for a particular application. So RFICs in particular all sorts of different functions are available in RFICs. You can get mixers, you can get amplifiers, you can get frequency synthesizers, modulators, demodulators, all sorts of different things, transmitters, receivers, but the one most integrated component that I imagine most of you would find useful for your designs is going to be a wireless transceiver IC. It's an entire transceiver on a chip. And I've listed a few part numbers here that are just examples of ones that I think are interesting that are on the market, but there are many, many more that could be useful for your design. So if your design is something that has, say, a microcontroller and you want to give it some kind of wireless interface to something else, This is the type of chip that you should be focusing on as being central to the RF part of your design, a wireless transceiver IC. They do it all. It's amazing how integrated these things are. Really is awesome. And you should try to find one that fits your application the best. Try to find one that is the most integrated so that you have the least other work to do in order to make it function. Now, I mentioned in addition to RF ICs, there's also like passive components, for example, filters that you can buy in an integrated component. Now, if you don't buy them in an integrated component, you have to build RF filters out of like capacitors and inductors, and there are tools to help you do this, like filter design tools that let you create this big network of capacitors and inductors and simulate it and try to figure out what its frequency response is going to be. And it's kind of a messy business because simulating these things requires actually like intimate knowledge of the properties of the components that you've selected, not just the capacitance, but much more than that, its frequency response. And also knowledge of the layout. Nuances of the layout can affect the performance of the filter in different ways. Let me show you my favorite filter design tool. Oh! I'm missing a slide. How did that happen? I'm going back and forth. Transceiver ICs, blah, 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 blah. It's totally not there. Okay. Oh, the moment is gone. My favorite filter design tool is supposed to be a screenshot of the searching for RF filters on DigiKey. That is that is my favorite filter design tool. Use your distributor's website. Use parts.io. Use resources that are online and available to you to find RF filters, because you can get a filter that, and we'll see one later on in one of my example boards, but you can get a filter that is just a single component and is not all these, and it's just one little surface mount component that you solder on your board, and it has a known performance, known frequency response, known impedance matching. It's super easy to use, and they only cost a few cents. And for almost any application, you're going to find a good filter. Look for RF filters. Also look for SAW filters, SAW, surface acoustic wave filters, for many applications, like something in an ISM band, like the 2.4 gigahertz band or the 900 megahertz band. For many applications, you can find a very low-cost SAW filter, and SAW filters are amazingly effective. They just have the most the sharpest cutoffs and the biggest difference between how much they attenuate the stop band versus how much they pass the signals that you want them to pass. Like, they're really good performing, and they're easy to use and low cost. So look for RF filters, look for SAW filters. I bet you'll find one that will fit your application very well. And it's a more integrated component that's easier to use than making a big network of passive components and trying to figure out how to put it together. So the next rule is use 50 ohms everywhere. So impedance matching is a thing. And we have these tools like Smith charts. This is actually a Smith wheel that you can physically manipulate. On the backside, it has a circular slide rule, which is cool. But so one of my former students sent me this as a gift. I think it's awesome, but I've never used it because because I avoid using Smith charts. I avoid doing impedance matching, which is one of the major uses of Smith charts. I avoid doing impedance matching myself. So impedance matching is a thing that you have to worry about sometimes in RF circuit design, but there's a super easy way to match impedance all the time, and that's just to use 50 ohms everywhere. Have 50 ohm outputs from every component, and then run that signal over a 50 ohm transmission line across your circuit board to a 50 ohm input on the next component. You don't need to worry about impedance matching other than just doing 50 ohms everywhere. And why 50 ohms? Well, I'm not going to get into the history of it, which I'm not even sure I know, but, well, I mean, I've heard rumors, but I'm not sure that I necessarily believe all the rumors. But we have a standard of 50 ohms in the industry. Almost any component, some components you might find have sort of random impedances, but any manufacturer that has paid attention to like trying to give you an easy to use interface to their component, any manufacturer pretty much is going to target the 50 ohm single-ended interface. Occasionally you see 75 ohms, like in the cable TV industry, but like in the cabling end of things mostly. But other than cable TV, almost everything RF is 50 ohms as a standard. So just go with 50 ohms. Everybody's using 50 ohms. You should use 50 ohms. And selecting components that give you a 50 ohm output is very easy. Selecting components that give you a 50 ohm input is very easy. Having a 50 ohm transmission line on your PCB is something that you have to take responsibility for, but it's pretty easy too. And what you need to do is to think about the microstrip impedance of or the characteristic impedance of a signal that's going on your top layer, some distance above your ground plane. If you have a component that gives you something other than 50 ohms, if you look in his data sheet and it says, like, I don't know, 34 plus 11J or something like that, and you're like, what is that? Don't worry about it. Well, first of all, see if there's another component you can use instead that does give you a 50 ohm impedance. But if there isn't, then just convert to 50 ohms right away. Just convert that signal as close to that component as possible into 50 ohm and then run 50 ohm trace across your circuit board. And how do you do that? You know what? I think I am missing more than just one slide. So I'm going to change things up a little bit here. Start over. No, we're not going to start over. We're going to flip through, make sure all the slides are here. You'll get to see the one that we missed, which is coming up. There it is, my favorite filter design tool. Woohoo! All right. Now, here we go. Transmission lines. Okay. So, if you have 50 ohm output and 50 ohm input, you still have to have a 50 ohm transmission line that goes from one to the other. How do you do that? Well, you use an impedance calculator, a characteristic impedance calculator for your PCB. How many of you have an impedance calculator on your computer? How many of you have KiCad on your computer? Oh, then you have an impedance calculator. How many of you have a web browser on your computer? Okay, then you have an impedance calculator because you can find tons of different impedance calculators on the web. Here's just one of many that I happen to like. It's simple and easy to use at mantaro.com. They have a whole bunch of different calculators that are useful for circuit design. And here's the things you have to plug in. You plug in the width of your trace in mils. You plug in the thickness of your trace in mils. Like how high is it? So, and the default is 1.4 mils. That's, it's a thin layer of copper. And then you have to have the dielectric thickness. That's the distance between layer 1 and layer 2. And then you have the dielectric constant, which is a property of that material, that substrate that the PCB is made out of. Okay, so where do you find these things? Well, you find them at your PCB manufacturer's website. So let's say you're using OshPark. You look up their 4-layer stack up and specifications, which are on the left here, and then you plug those values into the calculator. So your trace width, well, that's something that you get to define when you're making your circuit board, right? But your trace thickness, 1.4 mils. Oh yeah, that default actually is the same. Anything that's called 1 ounce copper is typically going to be 1.4 mil, and OshPark tells us that. Now, what's our dielectric thickness? 6.7 mils. That came from right here, 6.7 mil pre-preg layer between these first 2 copper layers, okay? That's where we got that number, and plugged 6.7 mils from the OshPark site into the calculator. And now, what is this dielectric constant? Well, it says down here, dielectric constant of 3.66 at 1 gigahertz. And the dielectric constant may change depending on what frequency you're working with, but if you look further down on this webpage, you'll find a link to the data sheet for this particular substrate material, and you will see that it hardly changes at all across a very wide range of frequencies. So you can just plug in 3.66 and you're fine. For other substrates, you may need to be a little bit more careful about what number you use at what frequency. So we plug in those numbers and hit calculate, and it tells us the characteristic impedance in ohms. And notice I've plugged in 12 mils, and it gives me almost exactly 50 ohms. So all I have to do, all this work was just so that I know my RF traces on the top layer of my circuit board should be 12 mils wide. That's it. And guess what? I only had to do that once. If I make many RF circuits and I use the same stack up, and I make everything 50 ohms everywhere, I only have to do this once, and I find out what my trace width is. Yes, question?
Just, what do you think it should be? 50 plus or minus what?
Oh, 50 plus or minus 10%. It's probably fine for most designs. If you're going like higher power, or you have really rigid performance requirements, you might have to go more precise than that, like maybe plus or minus 5%. But plus or minus 10% is probably totally fine for most designs, especially low power designs. So it doesn't have to be precise, but it has to be in the ballpark. If we made our traces 6 mil wide, things are going to go badly for us. If we make them 50 mil wide, things are going to go badly for us. But if we make them 12 mil wide, everything should be fine. Of course, a mil is a thousandth of an inch. So you can do this in units of millimeters if you want to, but most PCB houses do use imperial units, use mils. So that's usually what I use when I'm dealing with PCB specifications. So that's it. This is like the most complicated part of the talk right here. It's just using this PCB calculator. And you only have to do it one time, because all you're figuring out is how wide you need to make your 50 ohm traces on your circuit board. So what if you need something different? I talked about this just briefly before I realized that previous slide was missing. If you have a component and you need to use this, this component is perfect for your application in every way except that it doesn't give you a 50 ohm output. You need to convert that output to 50 ohms as close as possible to that component. How do you do that? Well, the traditional way that the books tell you about is to use the Smith chart and all kinds of stuff. But no, the way you do that is by following the manufacturer recommendations. Almost any manufacturer of RF components that gives you an input or an output that's not 50 ohms is going to provide for you the information that you need to figure out how to transform that impedance, how to convert it from whatever it is into 50 ohms. So let me give you an example. Here's the application circuit, like the first schematic that's that is present in the CC1110 data sheet. Now, the CC1110 is a popular wireless transceiver IC. It's the one that's in my favorite pink toy, the IME. And it's pretty easy to use, like most wireless transceiver ICs. And this diagram shows you everything you need to make its radio work. The only thing missing is some power supply decoupler capacitors. It also doesn't show you the digital side of things, like how does your microcontroller talk to it or something like that, but or how do you program it. But everything you need to make the radio function is right here. All there is this one funny decoupling cap over here, crystal oscillator, crystal and 2 load caps, this bias resistor, which is probably a precision resistor that they specify. And then over here we have this mess of capacitors and inductors that convert between this port, this 2-pin port, pins 23 and pin 24, over to a 50 ohm antenna. So this is the circuit that you can use to convert this to 50 ohm RF input and output. And since it's a 50 ohm interface, you can actually just replace that antenna with anything else. If you want to run a 50 ohm impedance trace over to some other component like a filter or an RF switch or whatever, you just plug that in right there because all this impedance matching is taken care of for you. Now we actually see, if you know a little bit, if you've ever looked at analog circuit design before, you might notice that there are a couple things going on here. This is actually a balun section, and this is a filter section here. Altogether, it effectively transforms the impedance for us, but it also gives us some filtering, and it gives us the balun function. Now, balun means balanced, unbalanced. A balanced signal is a differential signal. See how we have two signals, one's negative and one's positive? That is a differential interface. And then an unbalanced signal is also known as a single-ended signal, which is what we have over here. An antenna is typically a single-ended signal, and transmission lines that we use across our PCBs most of the time are single-ended signals, and that's what I recommend you use, 50 ohm single-ended signals. So this balun converts us to a single-ended signal, and this filter probably also transforms the impedance, and we end up with a 50 ohm interface. Now, this is the most complicated part, and the manufacturer tells you exactly how to do it. Now, as I mentioned earlier, these types of circuits, these bundles of capacitors and inductors, are very sensitive to particular component selection, and they're very sensitive to particular layout. So make sure you follow the manufacturer's recommendations very carefully. They will often recommend particular components. They will often give you the layout. They'll even give you Gerber files. They'll give you an example board, like an evaluation kit that you can buy sometimes, but they will give you the design details that you need, and you just copy that section verbatim. And I guarantee you that design will involve a 4-layer circuit board. So use that, follow the manufacturer's recommendation, and that way you can use something like this non-50 ohm, non-single-ended interface. You just transform it into a 50 ohm interface, and then you go from there. So the last rule is to route RF first. When you're designing your circuit board, route RF first. You should keep RF traces short and direct. So if you can put your components closer together, do that. You should, when I say short, I mean short with respect to the wavelength. How do you compute the wavelength? Well, approximately, the wavelength is going to be c, the speed of light, divided by the frequency. So if c is 300 million meters per second, and you want something running at 900 megahertz, that's 300 million divided by 900 million, okay, your wavelength is 1/3 of a meter. As long as your traces on your PCB are short with respect to 1/3 of a meter, you have nothing to worry about in terms of the effects of wavelengths on your design. Of course, that becomes a bigger problem the larger your design is. It becomes a bigger problem the higher the frequency is. But just do that in your head. Just remember 300 million divided by the frequency, and if that seems big compared to your circuit board, don't worry about it. Keep other signals away from the RF signal. Just make sure, don't run traces right next to your RF signal if you can avoid it. Just keep things keep a little buffer zone there. And characteristic impedance matters. We talked about that earlier. Make sure you use the impedance calculator and that you follow it. And every single RF trace that you have, every 50 ohm RF trace should be consistent with following what you learned. Now, you should route RF traces first, but of course you should route clock signals first, and you should route power first. But hey, power is taken care of most of the time if you're using the 4-layer stack up properly. Power, if you've never done 4-layer circuit board design and you do your first one, you'll be like, oh, this is so nice. Like, I just drop a via anywhere and there's my power. It's great. So you'll get spoiled very quickly. I sometimes use 4-layer designs for things that don't strictly need to be 4-layer designs now, just because it's so easy during the design process. So let's go through some examples. Those are the rules. That's all you need to know to be able to design your own RF circuits. Honestly, you'll have success. And let me show you how I've had success using these very rules in my own designs. So the first thing I want to look at is the GreatFET Project, which is new. Some of you have seen me carrying this around. This is the main board, Azalea, code name Azalea. It's if you're familiar with Travis Goodspeed's GreatFET project, this is sort of a next generation GreatFET, and it gives you a high performing, high speed USB peripheral. It gives you a device, like your own custom high-speed USB device that you can control from a simple Python interface on your host computer. That's one of the main goals of the GreatFET project. But one of the things we've been working on is different pluggable front ends, which we call neighbors, and plug in, and that's what some of these other boards are neighbors that you plug into the main board and give you some function. And one of them I want to look at is Crocus here, which is a 2.4 gigahertz wireless transceiver chip. 2.4 gigahertz wireless transceiver chip is probably something that could be used in a lot of your projects. So let's take a look at it. I'm going to zoom in on this board. Actually, I'm going to zoom in the future also, because I'm going to change to a newer rev of the board, the one that I just got, that has this SMA edge connector instead of the other connector we saw there. This is the entire RF section of this board. We have the NRF 24L01 Plus, which is a very popular, it's one that was mentioned in the slide I had earlier with different RF transceiver chips. It's a very popular 2.4 gigahertz transceiver chip from Nordic. And this entire circuit here, almost all of it, is taken directly from the manufacturer's recommendations. And there isn't much to it. There's this crystal oscillator, a couple of load caps, there are a few decoupling capacitors, there's this one bias resistor. That's a very common thing you see in these types of designs. And then look over here between the antenna connector and the antenna connector and the IC is this thing right here. This is a balun. Remember, the first balun we looked at was this complicated-ish schematic that had a bunch of capacitors and inductors. Well, you can do that, and the Nordic, the web page or the data sheet for this part tells you exactly how to do that. But instead, I actually went a simpler way. I Googled NRF 24L01 Plus balun, and I found two manufacturers that just sell a single component that's designed specifically to match the impedance, the differential impedance of this chip, and convert it to 50 ohms. It costs something like 20 cents. Instead of a mess of capacitors and inductors, it's kind of a no-brainer to use this thing. So you might be able to see, it's a little hard to see, but there's a differential pair here that goes from these two pins over to this balun, which is a transformer. A balun is a transformer. It converts this differential signal into this wider RF trace, which is 50 ohm characteristic impedance. Now, it's all jammed so close together that the characteristic impedance might not matter that much, but and I actually could move the balun even closer to the IC if I wanted to, but I sometimes, especially on a brand new design like this, when I'm prototyping, I'll separate things out just a little bit so I have more room to get my soldering iron in there, so I can drag solder that QFN. But look, that's all there is to it. Just a balun, one component balun, and a one component wireless transceiver chip, and then all I have to do is like give it a power supply and connect it to my microcontroller, and I can do radio stuff over this 50 ohm interface. Pretty cool. Let's take a look at another design. This is Ubertooth 1, which is a special purpose Bluetooth sniffer primarily. It can be used for other things, but the reason that I started the Ubertooth 1 project was because I wanted to be able to monitor Bluetooth communications. I wanted to be able to discover undiscoverable Bluetooth devices. And this is actually why I learned electronics, was so I could build Ubertooth. So let's take a look at this. We have USB, we have a big microcontroller, and then over here we have the CC2400, which is another wireless transceiver chip from the ChipCon family by Texas Instruments. Let's zoom in on this RF section here, from the transceiver chip to the antenna port, and see what's going on. Okay, so we have the CC2400. It has a few passives around it, exactly as recommended by the manufacturer. And then it has this CC2591 chip here, which is also recommended by the manufacturer. It's another chip that is a companion to the CC2400. Texas Instruments makes it, they're actually designed to fit together. And this gives you amplification, both transmit and receive amplification, integrated into one chip, which is pretty handy. And there is a differential interface that goes between the two. I don't have to worry about the impedance of that like not being 50 ohm single-ended, because these two chips are designed to connect directly together. So I just put them really close together, run those two pins to each other, and they match. There is an unused pad, a pair of pads here, where I could mount an inductor to repair the impedance match if it weren't good, but it's good because those chips are designed for each other. And then over here, this is the edge, this is the SMA connector over here, or actually it's an RP SMA because it's 2.4 gigahertz. Between there and the CC2591, there are inductors and capacitors. And how do I know how to build that network of inductors and capacitors? I found it in the CC2591 documentation in the data sheet and the example circuit that Texas Instruments provides, and I copied it exactly. That's all I had to do. The easiest part of the Ubertooth project in terms of the hardware design was the RF section, because it's all copied directly from the manufacturer. Now, including, it is important that it be copied very precisely. For example, there are these components down here, these passives, that have a particular transmission line length and width that goes, because the transmission line characteristics matter. And so the manufacturer actually specified like the PCB stack up and exactly how far this transmission line should be and so forth. So I copied it very deliberately, exactly like the manufacturer said, and it worked great. Now let's take a look at Yardstick 1. This is looks very similar to Ubertooth 1, same form factor, also a wireless transceiver chip on a USB dongle. And we just started shipping this recently, and it is for sub 1 gigahertz radio applications. So like 900 megahertz band or 300 megahertz, garage door openers, industrial control systems, smart meters, all kinds of stuff like that. And it's a really easy to use platform because it's something that lets you plug into your host computer and just control it from your host computer. It has a CC1111. We looked earlier at the schematic from the CC1110, another one of those ChipCon parts from Texas Instruments. This is the CC1111, which is the same as the CC1110, except it adds a USB port. So this actually integrates USB device, microcontroller, and radio transceiver, like a digital radio modem, all on one chip. The more integration, the better. And this one has a little bit more complex of a radio architecture. So let's go through it a little bit because I think it's instructive. So everything that's RF is from this CC1111 all the way over here to the SMA connector. Let's take a look, zoom in there and take a look at what's going on. So what's the first thing you see over near the radio chip? This. That's a balun. Again, I used a monolithic transformer, a single component, instead of a mess of capacitors and inductors. Now, one of the magic things about Yardstick 1 is actually that balun, and the only reason I knew about it was because I found it when I did the HackRF project. So, so this balun is not specifically designed for this transceiver chip, but it turned out to be very applicable to it. So I take this differential interface, and you see this a lot on these wireless transceiver chips or any chip that has a mixer in it. You see these differential interfaces, and you end up having to use a balun to convert them to single-ended. So right here we have about 100 ohm differential interface, and then immediately it gets converted to 50 ohm single-ended, and everything's 50 ohm single-ended from there on out. So what it goes through here, this is a capacitor, and notice it just goes through it in series. That's called a DC blocking capacitor. We'll talk about that a little bit. But RF goes right through it. So the RF goes right through there, and it hits this part, which is a switch. It is an RF switch. And now there are three paths to get from this switch to that switch. One path is this S-curve that goes directly from one to the other. Another path goes through this amplifier. Another path goes through this amplifier. There's a receive amplifier, a transmit amplifier, or a path that bypasses the two amplifiers. Remember in Ubertooth, I had one chip that gave me transmit and receive amplification all in one chip? That was super convenient. If you have the luxury to have the more integrated solution, go for it. It's great. But I didn't find a single component that did it for me, and so I ended up with this huge section, well, huge. We're looking at a few millimeters here. We ended up with this more complex section that includes two different amplifiers, two RF amplifiers, two RF switches, and methods for supplying power to those amplifiers. It's a lot more went into the design, but realize that every single component follows the rules that I was talking about all along. I have 50 ohm interfaces between everything, and I have as much integration as I can, and so forth. Now, on the other end here of this switch, we have, see this thing? Looks kind of like a ballon that we've seen before. It's not a ballon because it's single-ended in, single-ended out. It's actually bidirectional, so which one is in and out is kind of up to you. But this is a filter. Again, I'm replacing what could be a mess of inductors and capacitors with a filter. This is a low-pass filter designed for the 900 megahertz band. 900 megahertz is the highest frequency range that is supported by Yardstick 1. So I use a low-pass filter to cut out any harmonics that are above 900 megahertz, which is quite optimal when you're using Yardstick 1 in the 900 megahertz band. It's somewhat less optimal when you're using Yardstick 1 in lower frequencies, but it's a heck of a lot better than nothing. So I have an RF filter. I filter as much as I can of unwanted frequencies with one component that I found using my favorite filter design tool. And then I have this little structure here that allows you to provide DC power to the antenna port through an inductor. We'll talk about that in a little bit too. That's the entire RF section, all summed up here. So this is a lot more complicated, but it's still following all the same rules that I talked about earlier. They're the rules I follow for all my designs. Now, let's talk. Yes?
Why do you have different size vias?
Sorry? Oh, why do I have different size vias? That's a good question. So partly, I only have two sizes. It may be deceptive. You may think some of these vias are, like you might see more than two sizes, but it's probably just how much of the solder mask filled the hole. But mostly I'm using two sizes. I'm using a big size for power. So like, for example, here is a capacitor, a big decoupling capacitor. It has ground via and a supply via. And I want to have those vias be able to carry as much current as possible and be as low inductance as possible. So I use the biggest vias that I can. And then for signals that I don't really worry about the inductance much, or the current carrying capacity much, like let's say this one right here. This one is a control signal for that switch. It's simply take it high to have it switch one way, take it low to have it switch another way. Or it's actually more complicated than that because it's a multi-pin control mechanism, but that's the idea. And so those signals, I use a smaller via so I can squeeze things closer together. That's the only reason, is that I like to have bigger vias for power and smaller vias where I can get away with smaller vias.
Could you talk about the MITRE Tracers?
The MITRE Tracers. Oh, the corners, how I use 45-degree angles. So that's more tradition than anything. There are some myths about having signals like not go through 90-degree turns. Don't worry about that. But it does, I find, make the layout a little bit easier to work with if you're in the habit of doing things in 45 degrees. It makes some things kind of easier to fit together sometimes, like over here. I like using 45 degrees, but I'm not religious about it. So use whatever angles you want, pretty much. There was a good discussion of that on the Amp Hour, actually. Howard Johnson answered that question, or kind of debunked that myth a little bit on the Amp Hour. So check that out. So let's talk about components that I like to use on circuit boards, RF circuit design. And let's have a pop quiz. All right. Which of these amplifiers, these are amplifier ICs, which of these amplifiers should you use in your design? What's that? The one on the right. Why should you use the one on the right? It's internally matched to 50 ohms. What about the one on the left? Oh, the output is internally matched to 50 ohms. But the input is pre-matched to 50 ohms. What does pre-match mean? I have no idea. I think it's a euphemism for not matched. Take a look. Let's look at the BGA 777N7 on the left here. Let's look at it a little bit more closely. Look at this description down here. The device features blah, 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 matching off chip. It features matching off chip. You gotta love marketing people, right? Like, oh yeah, this apartment features a 3-mile walk to the nearest bus stop. You know? Think of all the exercise you'll get. So, right, so if you look further down, look for the recommended schematic. Always look for the schematic and see how easy is this part to use really. Okay, so here's the chip, here's the input, and yep, look at that. That's an impedance matching network on the input. You have to supply that impedance matching. Hey, and guess what? The output doesn't look like it's quite 50 ohms either, even though it said internally matched output 50 ohms. So here's another reason why you maybe shouldn't use this particular chip, which is, I think, from the same manufacturer as the other one. Manufacturer and part number, like, various. They don't tell you much about like which components you should use or how you should lay them out and stuff like this. So they're not particularly helpful. This isn't the most easy to use component. Now there may be other reasons why you want to use this component, but ease of use is not one of them compared to that other chip. Let's take a look at the recommended schematic for the other one. You have a power supply with a decoupling capacitor. Well, okay, you've probably done decoupling capacitors before. Easy. You have an input and an output, both of which go through a DC blocking capacitor, which I mentioned very briefly. I have some of those in the Yardstick 1 design and other design. There's a one capacitor on the input, one capacitor on the output. It's truly 50 ohm matched, both input and output. All you have to do is pick those DC blocking capacitors, and you're done. Now, DC blocking capacitors is something we'll talk about just briefly here, but in particular, I want to show you another kind of structure that you'll often see. This is from another RF amplifier data sheet, just something I happen to have on my laptop. And it shows you this structure called a bias T. You see this a lot, especially on the outputs of amplifiers. This actually has one on the input and the output. But what you see here is an inductor that carries DC power and delivers it to the amplifier that way. And then you see a capacitor that blocks that DC, a DC blocking capacitor. Now, that prevents that DC from going anywhere else. So the inductor here is called an RF choke. When an inductor is used for this purpose, it is called an RF choke. And when a capacitor is used for this purpose, it is called a DC blocking capacitor. Now, if you have not done much analog design, this may not come totally natural to you, but this is something that you need to get familiar with. That inductors and capacitors can be used in these ways. Capacitors, and this is how I remember it personally. Capacitors, you know, like from their schematic signal, they're two plates, right? Two different conductors that are isolated from each other. No DC can cross. So capacitors block DC, but pass higher frequencies, like RF, okay? So you can just stick a capacitor right in series in your RF signal, and the RF goes right through it, but it will stop DC. Inductors are the other way around, and again, I remember just by looking at the schematic signal, like this is a coil of wire going from one end to the other. It conducts DC from one end to the other, but it blocks RF. One of these things conducts RF and blocks DC, the other one conducts DC and blocks RF. So this is why you see this common structure called a bias T. It biases this section of the RF signal with a DC component that comes from this power supply. And that's how the amplifier actually gets its power. And then this DC blocking cap prevents DC from going other places and doing unexpected things. So those are two things. And you have to be a little bit careful how you select your inductors and your capacitors for these purposes. But look at the documentation provided by the manufacturer. You may not be used to looking at capacitor data sheets, but they exist. Some manufacturers are better at publishing these things than others. I happen to like Murata a lot because they have a lot of documentation about their capacitors. So I can download very great detail about how their capacitors perform at different frequencies. That's often what you want to know. You want to know, does it pass my frequency of interest really well? And does it block other things that I don't want, notably DC? In a DC blocking cap, what really matters normally is how well does it pass the frequency that I'm interested in. Same thing with RF chokes. Look at your frequency of interest. How well does this inductor stop the frequency of interest? You don't want your radio signal going into your power supply. You want your radio signal going out the output. And so that's how you select the inductor and the capacitor, is simply by looking at how much they pass or how much they block of your expected frequency. Here's another example that uses DC blocking capacitors. This is an RF switch. Remember I mentioned I had a couple of RF switches on yardstick 1? These components are typically pretty easy to use. RF switches. Now they do tend to come in small packages. The ones on HackRF are particularly hateful because they're 1 millimeter by 1 millimeter 6-pin QFNs. But you can solder them. And this is one of the things, like when you get into RF, you just have to start to get used to doing 4-layer boards. You have to get used to using 0402s. You have to get used to using QFNs because those are the best components for the job. But you will get used to them. You can do them. You can drag solder QFNs. Sometimes I cheat a little bit. Actually, often I cheat a little bit and just make my QFN pads a little longer just to make them easier to drag solder, especially for prototyping. That's really handy. You'll learn these things as you deal with these components more. But you'll see here, we have a DC blocking cap on the input, DC blocking cap on this output, DC blocking cap on this output, and then just 2 decoupling caps on the control voltages and ground, and that's all you have to supply. So the only thing complicated about using this part is just selecting the DC blocking caps. And usually in a design, you will find a DC blocking cap that's good and then use that same part for your whole RF chain, because most of your chain is probably going to be running at the same frequency anyway. So all you have to do is that effort once, and you're good to go. So these are all the different types of components that you'll probably use in your RF design. Even though I used amplifiers a lot because they happen to have some nice examples for impedance matching or lack thereof, and like bias T's and stuff, I don't actually recommend that you get right into using amplifiers. Don't use them if you can avoid them. But I do recommend that you use wireless transceivers, that use RF connectors. Capacitors and inductors are going to find their way into your design in the form of DC blocking caps and RF chokes. Switches are handy anytime you want to have a signal, like maybe you have 2 different antennas and you want to be able to switch between the 2. These RF switch ICs make that super easy. Balance and filters, look for those as monolithic components, integrated solutions instead of doing them. And look for all these things. So things that you want to look for in these components, some of them I mentioned already, but like ease of use is number 1 for me personally. 50 ohm interfaces, look for that. Look for, in filters, look for the frequency response. Look in the data sheet and look for the graph that shows you how much it passes the frequency of interest and how much it blocks other frequencies. Switches, let's see. Mostly that's just an ease of use issue, but you also look at the frequency response potentially of a switch. You'll also look at its insertion loss, like how much loss there is when you put that, Every step along the way in your signal chain loses power. How much depends on the particular components you use. So look for how much loss there is. Inductors and capacitors we talked about a little bit. Transceivers, again, it comes down to ease of use a lot of the time. What's the most integrated component for the job that you're looking to do?
How much attention do you pay to power ratings?
Power
Ratings of the components?
Oh, that's a good point. How much attention do I pay to power ratings of the components? Quite a lot. But mostly I pay attention to power ratings of the components only if I'm using amplifiers. Wireless transceiver ICs tend to be quite low power and tend to never be too much to overpower any of these other components except maybe amplifiers. And when you start dealing with amplifiers, you need to be careful of things like the linearity of the amplifier, and look in particular for what's called the 1 dB compression point. It's often called P1 dB. That is the amount of power that you can put through it and have it will kind of linearly amplify. You put more power in, it gives you more output. You put more power in, it gives you more output. You put more power in, it gives you more output. But then it starts to level out. You put more power in, and it gives you like 1 dB less output power than you expected based on this curve, this nice linear section. That's the point at which it stops behaving linearly. You generally don't want to exceed that point. And so pay attention to that. Be very careful, because sometimes the 1 dB compression point is specified for its input power and sometimes it's specified for its output power, and those are very different things. Also, it's sometimes specified as a third order intercept point instead of 1 dB compression point, and it happens to be about 20 dB higher than the 1 dB compression point. So there are a bunch of things like that that are complications of dealing with amplifiers that you generally don't have to think about when you're dealing with these other components. Also, anytime you're dealing with amplifiers, you run the risk of getting into trouble. Creating problems for other users of the spectrum, which are a lot less likely if you're doing low power stuff without any special amplification parts. Also pay attention in the amplifiers. Not only do they have a certain point over which they start behaving non-linearly, they also have a point beyond which you just damage them. So look at their absolute maximum input power that you can give them. So that's actually the most challenging part to select compared to all these others. Now, one thing before I go, I want to mention software-defined radio is a great tool for you if you're getting into RF circuitry, because you can use software-defined radio platforms as low-cost test equipment. Use your software-defined radio platform as a way to monitor the transmission that your device is producing. Use your software-defined radio platform to transmit a signal into your device, a test signal. Instead of having a bench full of tens of thousands of dollars of equipment, you can get away with a lot by having low-cost, uncalibrated test equipment like software-defined radio platforms. And software-defined radio is also a good educational platform for you to learn a lot of these things. So like, today I've helped you learn about components and how you piece things together and how you make your circuit board. But what about the architectural layer? How do you decide when you want to use a mixer? How do you decide when you want to use a filter? All these different sorts of things, like my structure of switches and amplifiers and filters and stuff that I had in Yardstick 1. Like, how did I come up with that solution? Well, the way that I came up with that solution was based on my experience with software-defined radio, doing things in software that now I'm doing in hardware. So use SDR as a way to learn about this stuff. I have a video series. It's free, open content that I'm working on. 10 lessons are up already on greatscottgadgets.com, and you can learn about software-defined radio. There's an entire lesson on decibels. So, we were talking about the P1 dB point, like it's specified in decibels for the amplifiers. If you are not well versed in decibels, go watch my video on decibels, and it's something that everybody learns as they're learning SDR. So SDR is a great resource for you that you can use both to test your systems and also to just learn more about how radio systems work. And I I think we're about out of time. Do we have any last questions before we go?
Have you had any users of FCC approved? Can you talk about that?
Oh, FCC approval. Okay. Oh boy. All right. So, Chris tells me I have 5 minutes, which might be enough to answer this question. No. And I'll answer it very briefly. The FCC process is complicated, and it depends very much on what kind of device you're dealing with. Now, if you want to sell a device that is a radio device in the US, you probably need to be dealing with FCC certification. You need to be specifically looking at the equipment authorization services of the FCC. Equipment authorization, that's what you want to look into. And however, there are exceptions. For example, test equipment, exempt. So that's how I'm able to legally sell HackRF1, for example, and other software-defined radio platforms. That's how, Anritsu and Agilent and, Keysight and everyone else is able to sell like benchtop RF signal generators. It's because test equipment is exempt. So if your project is test equipment, then you have a lot less to worry about, and there are similar exemptions in other countries. But if your project is not test equipment, and you're trying to get it to a point where you need to be able to sell it, then you definitely need to be looking into the equipment authorization rules of the FCC. Generally speaking, if you use those wireless transceiver ICs that I recommended, and you follow the manufacturer's recommendation, you're highly likely, and you follow these rules that I've given you, you're highly likely to have a design that can pass FCC compliance testing. And there are labs that specialize in testing your product for you and providing the documentation that you need to get your equipment authorization from the FCC. If you're rolling your own RF solution, you're not using one of these wireless transceiver ICs, you may have more trouble. But filter, and use the recommendations that I gave you in this talk.
How do you decide between regular antenna and PCB antenna?
How do I decide between external antenna and PCB antenna? Is that the question? PCB antennas are a thing. You can build an antenna structure into a printed circuit board. And external antennas are easy to support by putting a 50 ohm connector, such as an SMA connector or a BNC connector or an N connector on your board, something like that. I like SMA connectors a lot just because they work well at high frequencies, and I tend to like to do things over a wide range of frequencies. But there are other RF connectors that are perfectly good, and most of them are 50 ohm and are intended to work with 50 ohm impedance antennas. So when I choose to use an external antenna connector, it's usually because I want to give the user the option. I want to give the user the option to use whatever antenna they want. And when I use a PCB antenna, it's usually because I don't care about that option, or I'm trying to do things as simple and as low cost as possible, fewer moving parts. So for example, conference badge that has a wireless part on it, throw a wireless, a PCB antenna on it, and that way everybody can use it without having to like wear an antenna, which is more expensive, right? It's typically less expensive to go with the PCB antenna, but they're worse performing. So it's mostly a performance versus cost, or a flexibility versus cost.
When you do that, let's say you choose like a PCB antenna, do you actually clear all the layers underneath it?
You do clear the layers underneath a PCB antenna, and if you follow the manufacturer's recommendations on this, because some of the wireless transceiver chip manufacturers will actually give you PCB antenna designs that they recommend to connect to their device, use that. Texas Instruments has a good application note on where they tested a whole bunch of different PCB antenna designs, and you can see specific performance of these different designs, and you can copy those designs directly. So I'd recommend checking that out as well. Behind you?
Just to expand on that, what about a chip antenna versus PCB
Oh, that's a good antenna too. Sorry, good question too on antennas. That's a third option. You have the option of putting an external connector on. You have the option of having a PCB trace antenna. You also have the option of using a chip antenna, which is a single device that you solder onto your PCB that is an antenna. And sometimes there's a hybrid solution where you have like a chip antenna that requires some special PCB trace tail off of it or something like that. Generally speaking, it's the same sort of thing where it's a cost versus performance issue, but it also is a size issue. If you decide you don't want an external antenna, you definitely want to go with chip or PCB trace antenna. You're trying to decide between the two. Usually, a chip antenna will give you better performance per board area than a PCB antenna will. A PCB antenna will tend to take up more board area, and that is the trade-off usually, in my experience, is that it's performance versus board area. All right. All right, thank you all for coming.